we'll get started here. So question A, part A is increasing and decreasing. So you have to take a derivative. You should know that by now. I mean, you're in calculus. You got to be able to take a derivative. And that's why it was emphasized so much. So to figure out where it's increasing or decreasing, you have to take the derivative and then set it equal to 0. And this is now a test of your prerequisite skills, you know, what you learned in other classes. You have to be able to factor. You have to be able to do all of this very quickly. Okay. And you find the critical points. You say, okay, where does this thing equal 0? It equals 0 at 2 and -3. Those are your critical numbers. Okay. And then you make what I call a sign chart, number line, and you put those two values on the number line. Okay. And then you're supposed to use what are called test points. Any of this sounding familiar?
Yes, sir.
Okay, so you test points in each of these three windows. So the part here that most students find confusing, and I'm try really hard here to make it not, is you don't actually care whether the number is, you don't actually care what the number is. You care whether it's positive or negative. So look at this factored form. Okay, look at this factored form. We got 6 times x plus 3 times x minus 2. We're going to start with 5. Is 5 plus 3 a positive number? Well, it's positive. 5 minus 2, is that a positive number? It's positive. What is a positive times a positive times a positive?
Positive.
Positive. Okay, let's go to 0 here. 0 plus 3 is a positive. 0 minus 2 is negative. Positive times a positive times a negative is a negative. You do not need to calculate what it is. You just need to know whether it's positive or negative. -5. -5 plus 3 is negative. -5 minus 2 is negative. Negative times a negative times a positive is a positive. Can't emphasize that enough. You only care about whether it's positive or negative. So you only care whether you're multiplying two positives, dividing, positive, negative, all that stuff. Okay, so now it is increasing in the positive window. Okay, so let me scroll down here and it is increasing from, and this is minus infinity to infinity, minus infinity to -3, comma, 2 comma infinity. Because it's positive in there. And then it's decreasing in the other interval. It's decreasing from -3 to 2. Is that okay?
Yes, sir.
All right. So now part B is to find, and I'll snip this in because it's a little bit harder. It's to find the local max and local min. Okay, so to find the local max and the local min, we have to first give you some definitions. Okay, if it's increasing to decreasing, sorry, yeah, and let me put the words here: increasing to decreasing. Okay, this corresponds to a max. So graphically, and I'm going to use a color here. Increasing means it's going up. Decreasing means it's going down. That sure looks like a max to me. And a min is the other way around. So a min is when you go from negative to positive, decreasing to increasing. This is a min. And again, graphically, like if it's decreasing, things going down, then it's increasing, it's going up. Well, that sure looks like a min there. The other two possibilities, excuse me, are a plus to plus or a minus to minus, and these give you nothing. Okay, so if you got all that down, I know I'm gonna have to do that really quickly. We're gonna go back and look at the sign chart. But the key here is understanding these first two. If it goes from plus to minus, it's a max, minus to plus, it's a min. Okay, so let's go back and look at the sign chart. So plus to minus, that means the function's going up and then it's going down. So -3 is a max. It's max. Okay, and at 2, it's going down, then it's coming up. So that's a min. Okay, But the problem is you have to do more than that. Like that's just the X value and the Y. Those are just the X values. So I know I'm scrolling to do a lot here. So you have a, what did I just say? You have a, sorry, I just lost track what we're doing. You have a max at X equals 3. You have a max at X equals -3. To get the Y value, you have to go back to the original. And you have to put that value back into this function. So the -3 goes back in each of those. So you have to find out, you need the Y value, 2 times -3 cubed plus 3 times -3 squared minus 36 times -3, or whatever that is. Like that's not important. It's like all knowing all this stuff. So now the other one is the min at X equals 2. Same thing. You have to find f of 2 and so on.
And those give you your max and minimum
Yes.
values.
Yes, but you know ahead of time that's a max or min, not because of what it is, but because of this sign chart back here on the derivative.
Okay.
All right, now part C. Part C, intervals of concavity and inflection points. Okay, so to do this, you need the second derivative. Okay, and I'll make this more compact in the next one, but we want to go back to the line that is not reduced, believe it or not. You want this line right here from your derivative. That's where you go here. Okay, and to find the second derivative, you just use the same rule again. Power rule again. So it's 12x plus 6. You set this equal to 0, and you find that x equals -2. This is also a critical number. Okay, make a number line again. This is now the second derivative number line. Okay, and then you test values. Okay, and I'm emphasizing this by doing it in blue, but you know, you just have to test, and we only care whether it's positive or negative. So number smaller than -2, like -10, number bigger than 2, like 0. Always try and use 0 if you can. So 12 times 0 is 0 plus 6, that's a positive. -10, -120 plus 6, that's a negative. Okay, so here's what this tells you. When it's negative, it's concave down. When it's positive, it's concave up. Okay, and then finally here, an inflection point occurs if plus to minus or minus to plus. That's the only time you'll see an inflection point on this.
All right.
So that's, I mean, that's really everything. Now it's like we do a bunch of problems and see if any of that made sense.
So
Okay.
the inflection point is at -2.
It's at -2 that sometimes you'll see like IP for inflection point. It took me forever to realize what the instructors are saying. And then you have to evaluate it again. So you have to go back to the original function and evaluate that. Okay.
What do you mean?
Like you have to get the Y value. A point is both X and Y. So you have to, it's an IP. Let me stop doing that in red.
So if it's asking for the IP, you get the X value, which is -2, and then you plug it back in to get the full answer.
Get the Y value. Yes.
Okay.
So like if we were to graph this thing, there's like 3 points that we care about, and that's where we're moving to in the next section that you sent, where you use all this information to graph. Let me just, if you give me just a moment here to get this minus 100 to 100. Yeah, let me try and show you all these points. -2, -2, -68. And I'll try and I'll snip this in. I think this will make a bunch of sense here. Come on, give me those points. Label, and then label, All right, so let me snip this in. Okay, so here's the graph of this function, and it's everything we just said. Okay, it's increasing all the way to -3. It's increasing from 2 to infinity. It has a max at -3. It has a min at 2, and there's the y value, there's the y value, and then this inflection point is at 68.
Okay.
And you can see, like, maybe you they I don't know if they still do this. So concave up means it holds water, and concave down does not. So, like, starting here at this place right here, like, do you kind of see how this holds water
Yes. Yeah.
and the other one does not?
Yeah.
Now, if I were to estimate, I would have estimated it there, but it's close enough. Like, visually though, it should make sense when you get your numbers.
Uh-huh.
Okay, so you're going to get an exam question just like this, where it asks you to do all these things. It's almost always a polynomial, but we can do as many more of these as you would like. I mean, you could see that took 13 minutes, so we may want to only do one more. Or
yeah, can we do number 5?
Yes, let me get that pulled up here. 5. Ooh, picked a good one.
Oh god.
Yeah. So 5 is a trig function. That's where you got to know your unit circle.
Yeah.
Okay. Sine x plus cosine. So this is like, it's telling you, like, only from 0 to 2 pi. Okay. So the right way to do this is to just take a first derivative and a second derivative right away. So sine x, derivative of sine is cosine x, derivative of cosine is sine x. Set this equal to 0. This is equal to 0 when you just do this over here, when sine x equals cosine x. So where does that occur in the unit circle? It occurs when it occurs there, and it occurs over there. So at x equals pi over 4 and 5 pi over 4. Okay. Then you got to take a second derivative of this. Cosine is minus sine x. Sine x, derivative of sine x is cosine x, equals 0. And when you solve this, you factor out a negative, or you move some things around here. Basically, it's when like, either you can either think of this two ways: either when sine x equals negative cosine x, or when cosine x equals negative sine x. They're both the same, by the way. Okay. So what does that mean? It means they're opposite signs. Well, that happens in the second and the fourth quadrant. So this is at 3 pi over 4 and 7 pi over 4. Okay, and you can look those up later if you need to, but that's the information we need here. Okay. So now we can go through and do it, like, and like, this is like a baseline. Like, you have to do all this before you can do anything else to answer these questions. Now we can actually snip in like what A wants and do it. Okay. So increasing. So that means we're looking at the first derivative here. Okay. First derivative. Now the previous example, I let this number line go on forever, but in this one, we know it goes from 0 to 2 pi, because that's where it ends. And there's pi over 4 and 5 pi over 4. Okay. And we got to figure out, like, well, what's going on here? Like what's going on in each of these intervals here? So this is where it's like more confusing, because, like, oh god, I can remember my unit circle and what's going on here. So let's test some points here. Let's test like 0. Okay. And then these are kind of not great, but let's go with like 3 pi over 2. Okay. That's a good one. And then this one's really tough. Like, we'd have to go with like pi over 6 there. Okay. Now, do you have a unit circle handy, or
I do.
not? You do. Okay. So in the unit circle, what's the value of cosine at pi over 6?
Square root of 3 over 2.
Right. And sine of pi over 6 is 1/2. Which is bigger, square root of 3 over 2 or 1/2? Hopefully you say square root of 3 over 2. And that's why this is positive here, because cosine minus sine there is positive.
Okay.
I'm sorry, I put the wrong number. This is pi over. We should use pi.
Okay.
There. Sorry. Okay, so pi. Now cosine of pi, unit circle, that's all the way on the left side. That's the x value there. It's -1 minus sine there is 0, so this is negative. Now at 3 pi over 2, cosine, again, we're looking at this one right here. Cosine is 0, sine is -1, negative of a negative makes a positive. So you can see it's increasing here. I'm sorry, decreasing there and increasing in the other interval.
So why is it negative in the middle? I'm sorry.
You're just evaluating this thing at pi. Cosine of pi is -1. Sine of pi is 0. -1 minus 0 is negative. Okay. And if you found the critical points correctly, you only have to test 1 point. If somehow you've gotten them wrong, then you might get conflicting answers. So that's why this is so important here.
Okay.
Okay, is that clear on that front?
I have a question on. Hang on.
We got B to do, but like, is that okay so far?
I got a question on the first derivative one, the critical numbers.
Okay.
How is it pi over 4 and 5 pi over 4?
That's the only place where sine and cosine equal.
That's value. They don't have to equal the same, like sign, like negative or positive.
They do. So it's like, if you look at pi over 4, both sine and cosine are the same. They're both positive.
Oh, yeah, okay. Okay, I got it. All right, that makes sense.
Okay.
Yep, I'm good.
All right. This is actually more about the unit circle than calculus, just this particular question.
All right, I'm ready for part B.
Okay, part B, and we actually just look at the same thing. It says find the local max and local min. So based on this sign chart, where it goes from positive to negative, is that a max or a min? Positive means it's going up, negative means it's going down.
It's a max.
It's max. Okay, so you would say max at x equals pi over 4. And then you got to evaluate. So it's sine pi over 4, more unit circle stuff, plus cosine pi over 4. Okay, so that's square root of 2 over 2 plus square root of 2 over 2. And so and sometimes you have to summarize this. It's a maximum of, this equals square root of 2 at x equals pi over 4. You have to write this kind of summary, sentence here. Your whatever you put at the end of a body paragraph, transition sentence or something. So, and how about the other one? So let's go back to the other one. What's going on here? Well, it's going from negative means it's decreasing, to positive, increasing. So this is it's a min. It's a min at 5 pi over 4. So we got to evaluate 5 pi over 4. So sine 5 pi over 4 plus cosine 5 pi over 4. Okay, and it's negative square root of 2 plus negative square root of 2 over 2. So it's negative square root of 2. So you would say min of negative square root of 2 at x equals 5 pi over 4. But don't let this fool you. It's not always, flip of the sign. That just happened to be in this case.
So why is negative, why is it equal to negative square root of 2?
Over here on the right. Yeah, you have to evaluate the original function. Sine of 5 pi over 4 plus cosine 5 pi over 4.
Right. Could you just go through the process real quick of how it's?
Sure. You're just looking at the unit circle. So again, here, if you don't have your unit circle down, you're gonna hate this. But I'm
talking about when adding those two. Oh, how is it negative pi over 2?
I see. So they're both negative. So that's where the negative comes from. It's half of something plus half of something. Half of something makes a whole. That's where the 1 is. Root 2, root 2. Like if I asked you what x over 2 is plus x over 2 is, you might say 2x over 2 and then simplify it to x.
Oh, okay.
And I'm sorry, that's what I skipped there. It's half of half. Half makes whole.
Okay, I get it. That makes sense.
Great. Okay. Part C sadly is just as much work as A and B. But at least we have the second derivative. So let's go back and get the second derivative here. Let's get all this stuff right here. And because inflection points refer to the second derivative. Right. So now we build another number line here. We started at 0. We go to 2 pi because we were told in the beginning that that's where it is. 3 pi over 4, 7 pi over 4. Now, whenever possible, try to pick the nicest points on the unit circle, meaning places where it's a nice value, like pi. Okay. Unfortunately, we don't get 3 pi over 2 here. So this one's kind of horrible. Like 11 pi over 6, maybe. It's not great. Over here, though, we can do pi over 2. Okay, so you're looking at the, and you always go back to the original. So what is sine of pi? We're gonna do this middle one first. Pi, sine of pi, that's on your unit circle. That's, over there on the left, right there. What say you? What's the value there?
Oh, you're asking me?
Yeah, if you want. That's the y value there is 0, so negative 0, 0. Cosine of pi is -1, but you have a negative there, so this becomes positive. Like there's 1, 2, 3, 4 things you got to take into account there. So that's why, if you got time, maybe you go and do a whole review on the unit circle of this.
Yeah.
Let's do pi over 2. That's up here. Okay, sine value up there is 1. That's nice. -1. Minus cosine of there is 0. So that's negative. Okay. Now there tends to be an alternating thing, especially with sine and cosine. Like I wouldn't use that as a justification here, but like this one does end up being negative. If you go to 11 pi over 6, you will see that. Okay. So at 11 pi over 6 on your unit circle here, right here. Okay. The x value here, okay, whatever it is positive. So this is negative of a positive. So that's a negative number. The sine value is negative, but it's not as, and that makes it positive, but this one is more negative than that. So that's why this becomes a negative. A lot of students use a calculator here. I know you don't have one, but if you're checking yourself, you're welcome to do that. So an inflection point occurs when you go from negative to positive or positive to negative.
So if it's a positive to positive, for example,
it's nothing. Yeah, it's
can't
nothing.
get an inflection point.
No. And now you got to remember that because you'll get something on a test or quiz that's an exception. Okay, so the next thing to do here is to evaluate these back in the original if you want. Okay. So that there's an IP at x equals 3 pi over 4, and the original was sine 3 pi over 4 plus cosine 3 pi over 4. I think, is that the original? Yes. Okay. So that is that one ends up being square root 2 over 2. This one's negative square root 2 over 2. So the inflection point has a y value. It's a point. So it's 3 pi over 4 comma 0, because this equals 0.
And then you do 7 pi over 4 to find the other one.
Yes, it ends up being the same value.
Oh, okay.
Same thing. It's negative root 2 over 2 plus root 2 over 2 equals 0. So
okay, I want to do some 4.4 ones.
Good, because that's a lot. There's a lot there.
Yeah,
a lot there.
Yeah.
All right. So you actually did these problems in pre-calculus at some point in your life. You're just doing them now with calculus. So it's like finding the information by hand that you used to either go to your calculator for or Desmos for. So it's really painful. Yeah. Which one do you want to do? We'll be able to do a couple. The nice thing about these is you can always check them, using Desmos or something, but you got to do everything by hand like that. You want to avoid doing that if you can. So where do you want us to start here? What
Let's do number 3.
number 3? Okay. So depending on whether it's a polynomial or a rational, you do a few things, same or different. Here, here you want both the factored and the non-factored form, like this, okay? Because the first thing you're gonna do is you're gonna find the zeros. Okay, so there's a 0 at x equals 0, or when x cubed minus 4 equals 0, which is the cube root of 4, which we don't know what that is, but it's somewhere between 1 and 2.
Well, don't you take the derivative to find the zeros?
No, this is precalculus stuff. This is like before you even do derivatives, you know to do this. And that's what I mean. Like, you can think like, oh, there's there's a lot you can do here without ever doing calculus, but there's one at 0, and like I said, somewhere between 1 and 2. We'll say right there is the other one. So you can also find the y-intercepts. And believe me, this is stuff you're actually supposed to do. That's when x equals 0. You actually already have that on this one. Then you want to find end behavior. Okay, so end behavior is like, oh, what degree polynomial is this? What's a 4th degree polynomial? That means it either starts high and ends high, or it starts low and ends low. Because the leading term is positive, it starts high and ends high.
Okay.
And this is just one section. So some of these things you're like, oh my God, I forgot this, or I don't remember. Like, it's just one section. Like you did.
So if it's negative, it ends high.
It ends low. Starts low and ends low.
Doesn't matter if it's like positive or negative.
It does.
It doesn't matter if it's even or odd. My bad.
Yes. Yes. Okay.
Well, what would it look like if it's odd?
Okay, so there's 4 graphs that are possible here. So I usually do this. We're gonna run out of room, but so it's like this. If it's degree even, A positive, A negative. A is that leading term there. Even is up and up. Odd, negative is down and down. And then if it's odd is down here. A positive. That's like a cubic. So it starts low and ends high.
Mm-hmm.
And a negative cubic starts high and ends low when A is less than 0. You have to know these 4 graphs. And then rationals are totally different, but they
Okay. All right.
So next is derivatives. We're finally up to derivatives. There's some other things here like asymptotes and stuff like that, but we don't have any of that in this one. So the derivative of this is 4x cubed minus 4. And you set that equal to 0 and you find critical points. So this is difference of cubes. This is review. This is probably something you haven't seen in a while, but it is there. So this has this has a critical point at 1. Do you see that? Because that's the only place that equals 0. Okay. All right. And then
you can't factor the other one.
No, the other one's totally done. So from here, that tells you that there's a critical number at 1. And see, I got to move all this down because we got all this stuff going on. Let me move all this down if I can. Okay. So you have to make a derivative line where there's a 1 there. That's minus infinity to infinity. This is your y prime. So we're trying to figure out what happens left or right of this number. So we can test some points. So let's test 0. This is negative. This is 0, 0, positive. So we have a negative times a positive. That's positive there. So this is negative. And then this is positive. You can test a point. You know, whatever, test 5 there, and then you'll get a positive. So that means it goes from decreasing to increasing at 1. So that's going down and then going up. So this is a min at x equals 1. To get the y value, you have to go back to the original, which is 1 to the 4th minus 4 times 1. That's -3. So at 1, -3, that's a min. And you might even write that there so that you can help get that.
You can't get any asymptotes from this.
Or not. Yeah, there's none on this one.
Okay. Why is that?
It's a polynomial. There's no division. You only get asymptotes when you have division.
Oh, yeah, right.
Yep. Okay, so now we got to find the second derivative. So we got to scoot all this down again. One limitation of this. So we have to find y double prime. Now you don't want to go to this line here because it's product rule. We don't want to do that. We want to go back to this line, 4x cubed minus 4. So the second derivative is 12x squared equals 0. This equals 0 at 0. Okay, so here's our inflection point, maybe, right? Maybe. We got to check on whether it goes positive or negative to positive. So when you test a negative number back here in this one, you get a positive. When you put a positive number in here, you get a positive. Is that an inflection point?
No, sir.
No, and that tells you that it's concave up everywhere. So that's kind of hard to believe, but let's take a look at that. Okay, so concave up. Now you can so it's concave up everywhere, right? So we actually have enough to do this. So it has to connect at these points. Do you get that? Like it's
Yep.
okay. So like, and this is where your curve sketching kind of like looks really crappy, but like you have to connect the dots here. So that's concave up. That's concave up. This is weird, but it's a min, so it's concave up though.
Right, it's just a weird looking graph.
Right. So because I've it doesn't look like this at all, but like if you use a nice piece of software, you get this is what your instructor is looking for. They're looking for all this work to lead you to that place.
Okay. And we're done with that one.
That's it. Remember, we're done with that one.
Okay. If we get lucky, we may be able to do 2 more. I want to do number 9 and 11.
We can do 9 for sure. These are better because you actually just, like I said, you just graph them and you look for the stuff. If you're like, oh, where is that? And then you kind of can visualize it. But yeah, we'll see. I gotta drop this down below this other one. So yeah, so this one has a few more things that the previous one didn't have.
Yeah,
This one's got some restrictions, right? It's got a vertical asymptote where the bottom equals 0. So at x minus 1 equals 0 or x equals 1. So when you graph that, you want to graph as you go, by the way. Don't wait till the end because you will not like what you did. Okay, now this one also has a horizontal asymptote, and this is precalculus. It's the ratio of these because they have the same degree.
Mm-hmm.
So it's y equals 1 over 1, which equals 1. So there's your horizontal asymptote.
Could you go over the rules of the asymptotes real quick?
Sure. So case 1, the degree of the numerator is less than the degree of the denominator. So an example of this would be y equals x over x squared plus 5. See how the degree of the numerator is 1, the degree of the denominator is 2. This is always y equals 0, always.
Okay.
Case 2, that's what we just did. The degree of the numerator equals the degree of the denominator. And an example of this is y equals 5x to the 8th minus 7 over 7x to the 8th plus 3. It ends up being a ratio.
So it'll be 5 over 7.
5 over 7. And then the third case, which isn't important here because it ends up being a slant asymptote. Let me see if it applies to any of the problems. Doesn't look like it applies to any of these. But the case 3 is when the numerator is greater than the denominator. That leads to a slant asymptote.
Okay.
Okay, so kind of out of scope here, but that is what we've got. Okay, great. We still have to figure out where this thing equals 0. I'm sorry, where the x-intercepts are. The x-intercepts is when y equals 0. So when you write 0 equals x over x minus 1, it ends up just being where the numerator equals 0, which is at 0.
Okay.
Okay, now the y-intercept, whenever it gets there, that's also the x and the y-intercept. Okay, so we don't. So sometimes you do the y-intercept, but that's when x equals 0, and that's 0 over 0 minus 1. It's 0 over -1. It's 0, but that's it. Okay, now we go and take the derivative. Okay, so we got to take the derivative. Which rule are we going to use for that?
Quotient.
Quotient. Right. Not exciting. So y prime is bottom times derivative of the top minus the top times the derivative of the bottom over the bottom squared. You have to simplify now. X minus 1 minus x. So this simplifies to -1 over x minus 1 squared. Now normally you set this equal to 0. The thing is you could work on this for a while. It never equals 0, but it does have an issue at 1. So 1 is not a critical point. It's not a critical point, but it is like a place where the function is not defined, because we just said that back in the graph. Remember, we said, oh, it can't be 1. But you have to conclude that it's a barrier or a place. So you're looking for both critical points and places where the derivative is not defined. So like another step, another layer here. So that's at 1. We need to test, I don't know, we're going to test 0, always try 0, and then 5. And we're looking at the sign of this again. So if you put 5 in, you have a positive number squared. Negative over positive is negative. If you put 0 in, you get a negative number squared, positive, negative over positive is that. So it's decreasing everywhere. It's decreasing. That's what this means, decreasing everywhere. And that's what you have to take away when you do this. Like, oh, it's decreasing everywhere. All right, so like we can't connect the dots yet, but well, it ends up looking like something like this, but maybe you don't know that yet. So now second derivative, right? We got to find y double prime. Okay, and y prime is right here. That's why you simplify it. Y prime can be written like this. I know I'm going really fast, but some of this you already know, so you can just look back later.
No, you're good.
This is 2x minus 1 to the -3 power. Okay, derivative of the inside function is 1. So this simplifies to 2 over x minus 1 cubed. And again, you would normally set this equal to 0. It's not equal to 0 anywhere, but at 1, it's not defined. So it's not a critical point, but it's a place in the domain that does not exist. So you have to consider that as well. So let's test 0 again and 5. Okay. And what we find is at 0, it's a positive over a negative. And here it's a positive over positive. So this is concave up, this is concave down. And that's how you finish out the graph. So it's decreasing everywhere. So is this decreasing? And is that concave down, what I just drew? Yes, it is. Is this decreasing? And is it concave up? Yes, it is.
Okay.
So the shortcut here is if you had a calculator access to something, you graph it, but then you show all your work like we just did here, and kind of like, wave your hand and act like you did it. It's truly a lot of work to do this correctly. But what I know you can do is I know you can take derivatives, find critical points. It's really this last step of graphing that's really hard to do. Now you said 11.
Yes.
All right. Please don't be overwhelmed by this, because you can you can actually do this, and they only give you one on the test. I mean, it's not like it's a full test.
Yeah. It's making all sense to me. I just gotta practice.
Yes. Okay. All right. So pre-calculus stuff. So first thing we're gonna do is factor the bottom. It's difference of squares. And that tells you, there's vertical asymptotes at x equals 3 and x equals minus 3. Okay. So I'm going to graph those first. Minus 3, positive 3. Okay. Now, what is the horizontal asymptote? Well, what's the degree of the numerator? There's no x, so it's degree 0. Denominator is 2. So it's got this right here. Okay. Now I didn't say this before, but I probably should have. You can actually draw little arrows at each of these because it's going to connect to one of those arrows when we're all done. Like if we do this, it's just a connect the dots game. We don't know what it's doing quite yet, but we're thinking it's going to do that. That's here. So, okay. Does this have any zeros? Okay, no, because the numerator, if you set y equal to 0 to find the x-intercept, 0 equals 1 over x squared minus 9. That never happens. Okay, because they're just not possible. But can you set x equals 0? Can you find the y-intercept? Yes. 1 over 0 squared minus 9, negative 1/9. So that's like right there. Like that's whenever you get a point, something has to connect to that point. And that's good. It's like, okay, finally something, I can connect to, like maybe it's this arrow connects to it or that arrow, I don't know yet. Okay. And then sometimes you have to rewrite this yet again to be able to take the derivative nicely. Like it's not a quotient rule, it's a power rule followed by a chain rule. So your y prime is
the y-intercept, would that be 1/9?
0, negative 1/9. Sorry, I skipped over that.
Okay.
Right there. So the y prime is negative x squared minus 9 to the minus 2 power times 2x. So it ends up being, when you simplify this, negative 2x over x squared minus 9 squared. Okay, and then you got to make your sign chart again. So you already have negative 3 and 3 in there because those are places where the function's undefined. But then this equals 0 at 0.
Is it negative x squared minus 9 because you moved it from the denominator to the numerator?
It is what? I'm sorry. Yes, because the negative power, you move it down. Yes.
Okay, all right.
Okay. So now you got to test 4 regions. So like -5, -1, 1, and 5. Okay, so we're putting them in here. This is another one of those like where you only care about whether it's positive or negative. The bottom is always positive because when you square, it's always positive. So it's just whatever the top becomes. Negative, negative, positive, positive. So this means it's increasing, decreasing, decreasing. At 0, though, it goes from increasing to decreasing. So that's a max. So this one connects like this because it has to be a max. Okay. Second derivative. Whew, this is horrible. Horrible. Oh man. Is this clear? I mean, is this okay?
Do you not have to do the other ones like negative 3 and 3? Or it's because they're positive, so.
Well, okay, so there's nothing there. Yeah, positive. And because they're broken by an asymptote, that's the problem. Like things don't matter. Like let's say this went from positive to negative, because it's broken by an asymptote, the rules change.
Okay. All right, I get it.
All right, now second derivative is horrible here. It's x squared minus 9 squared times the derivative of the top, -2 minus the top times the derivative of the bottom. 2x squared minus 9 times 2x over the bottom squared. This is horrible, by the way. You're supposed to simplify this, which we won't even have anywhere close to the amount of time to do this. But what you're going to find is that there is no inflection points, and then it ends up being that this looks like this, and this one looks like this. And I'm sorry I'm not doing the full like thing on this, but you would have to simplify this, and it's quite messy.
Okay. All right, we can end there.
You sure? I mean, I'm happy to either point out some more things or.
Yeah, we're good. I'm good.
Okay, thanks for scheduling. Again, please don't let this overwhelm me. I don't think it will, but I'll say it again.
Yeah, I just gotta practice.
You can do this. All right. Thanks again. Have a good night.
Can you send me these notes right now?
I'll do it right now. Thank you, sir.
Cool.
Okay,
All right,
bye.
thank you.